Hello, and welcome to the second of the timeline-based memory model diagram videos. This video is about the TSO memory model. And on the screen, you can see here a test program which is designed to show two features of TSO. So this is the program. And this is results that are possible with the TSO memory model. And they're actually quite surprising results. So if you look at the order of the program, it writes this flag, then writes this location, then reads the location, then reads the flag from the other processor. The other processor does the same, reading the flag from the first. But you'll look here that both of these can read the location that they themselves wrote and still get the initialized state of the flag from the other. So this reads the value of memory before this write happens, and this reads the value of memory before this write happens. But it also reads its own write to the A location. So that's what these results show, and those are the surprising results that TSO allows. Now there are some features of TSO that you can see on the diagram. There are two of them actually. So TSO relaxes some of the rules that sequential consistency has, and the first one is seen right here. TSO allows reads that follow writes to be reordered relative to those writes. So those are writes to a different location than the read location. So here the read is of location F2, whereas this write is to F1 and this write is to A1. And that allows this read to be brought forward. This read cannot be reordered because it's to the same location as this write. So this read has to follow this write. You can see the same thing happening in processor 2. So what you see right here is the program order. Here's F1 equals 1, followed by A equals 1, R1 equals A, and then you would have register 2 equals F2, but TSO has allowed it to be reordered. And R2 equals F2 ends up out here way in front. So that's one feature, is this reordering. The second feature of TSO that is different from sequential consistency can be seen right here. And this is what's called early read of writes. And what it means is that when a write followed by a read of the same location happen on the same core, the same timeline, then that local read can see the written value before other cores can see that value. Writes are split into two pieces. One piece is a write to the local memory, and the second piece is the write to main memory. And the feature is that this main memory can be shifted relative to operations that follow the write. If this read were pushed along this timeline and it ended up in between these two writes, then that read would have seen 2 from main memory, and if it was pushed one more, it would have instead seen 1 from the first processor. So that indicates that this line right here in the program can read either 2 or 1 depending upon where it ends up relative to the other operations in the total ordering. What's different here is that before, writes ended up going all the way out to main memory without the possibility of any other operations getting between the pipeline's write and the result ending up in the main memory. And sequential consistency enforces this. If you've got two processors, each has their own cache and a main memory, with sequential consistency, no other operations can get in between this write done in the pipeline and the write done in the cache and the value being seen in main memory. It may not physically go all the way out, but on the memory timeline, there's no way for other operations to get in the middle. So that's the second main difference between TSO and sequential consistency. So the two differences between TSO and sequential consistency are that reads that follow a write to a different address can be reordered relative to that write, and reads that follow other reads to a different address can also be reordered relative to those reads. So this reordering behavior is one of the differences between TSO and sequential consistency. The other behavior that's different is that in TSO, writes are split into two pieces. One piece is the write between the pipeline and the local memory, the cache, and the second piece of the write is between the cache and memory timeline. This may seem like a subtle thing, the fact that these writes being ordered before these two reads allows these reads to see different values. In many programs, that isn't going to show at all. There won't be any way to detect that behavior. But consider the case when there's some kind of instruction that establishes a tie between this timeline and this timeline. And the presence of that instruction in the program establishes a known order between particular positions in the programs that are running in the two separate timelines. And in that case, there's a way to tell that the two writes do in fact precede the two reads. And when reasoning from the program, for sequential consistency, or for atomic writes, one would then expect those two reads to have the same value. And this split write feature of TSO would give a different result than what the person analyzing the code was expecting. And that basically brings up the last point of this video, which is to summarize the value that the timeline diagrams bring. And that value is to make it easier to reason about the behavior of a program. Once the rules for permutations have been established by checking those permutation rules against the actual hardware behavior, one is then disconnected from the hardware and free to only consider moving these operations around and rearranging according to the rules of the memory diagram, which were separately verified. So now it's much easier to look at these operations on these various timelines and to move them around to see what's going to happen. So for example, let's say as a coder, you are interested in determining whether it's possible for both of these registers to end up with the same value. Right? Here we have a permutation where they have different values. So what about the question, is it possible for them to have the same value? And look at the diagram. Well, we're free to move these values on this timeline. So it's easy to see that this one can be moved over to here. This one can also be moved over to here so that both of these writes hit main memory in this vertical slot here. The rules for these reads are they drop down and pick up the most recent write to the address that they're trying to read. So in this case, this read here, as shown, vertical line drops down and then go left, and there is nothing in the main memory timeline, so it picks up this write in its local cache timeline. But if these two had been moved so that they're both in between this write and this read would drop down, it would go along the main, and it would pick up the first of these writes, which is writing the value 1 into A. And so this read would pick up the value 1 from location A. And likewise, both those writes are also in between these two. So by the same rule, drop down vertically from this read and then go left, and it would pick up that same A with the value 1 on the main timeline. And that would be the value read into this location. And compare that to simply looking at the code and trying to figure out that these two registers can end up with either the same values or different values. It's not obvious. And hopefully after this tutorial, it's clear that working with a diagram with this visual information tends to be much more intuitive and much easier. So that concludes the video on timeline diagrams for the TSO memory model. And thanks for joining me.